Hello everyone, my name is Sondes ABDERRAZEK. I'm a freshly graduated doctor from Avignon University, and I did my PhD under the direction of Prof. Corinne Fredouille. And today I'm going to present to you my PhD work, which is on the application of deep learning, interpretability and explainability in a clinical context on speech pathologies. So actually this work is a collaboration with expert phoneticians, with a doctor from actually it's me, Corinne Fredouille is the thesis director, Muriel, Alain, and Christine are expert in phonetician experts, and Virginie Voisard is a doctor, ORL doctor. And this work is part of RIGBY project, which is a project aiming to invest in artificial intelligence for healthcare. So this presentation will be structured. First, I start with an introduction. Then I will give you an idea about the related works to this work. I will specify the goals and datasets we used. Then I will detail the proposed methodology, and finally I will conclude. So we are working on the context of speech disorders which affect the ability of a person to form correct sounds. Speech disorders can be due to neurological diseases, head and neck cancer, or other reasons. So basically, patients with speech disorders are significantly less intelligible, which affect their quality of life in general, especially when it comes to having a conversation. That's why assessing speech disorders is a crucial measure to monitor the progress of the pathology, to evaluate the effectiveness of a speech therapy, and to understand the effects of a particular treatment. In clinical practice, perceptual measures are the most commonly used method to assess speech disorders. It consists on a speech therapist which accord different scores to the patient to assess his or her speech quality. So here in this work we focus on the intelligibility, which is defined as the degree to which a person's message can be understood by a listener, and severity, which is the degree of the overall alteration of the speech signal. Now, the reliability of perceptual measures is affected by many factors, including the expertise of the expert, his familiarity or her familiarity with the patient, with the pathology, with the linguistic material on which he or she assesses the patients, etc. All of these factors reflect subjectivity criteria of perceptual evaluation, but also they are time-consuming and non-reproducible. So as a solution to these perceptual measures, we have a lot of automatic speech evaluation methods that appeared, and in this work we focus on the methods that are based on deep learning. So all of these automatic speech evaluation methods have the goal of an objective assessment of the pathological speech. So basically there are many works in the literature which take a speech signal and outputs a score for assessing this speech signal which belongs to a patient. These methods are seen as a black box, so there is no interpretation, so there is no deep learning explainability and interpretability. They do not take it into account, but also they just predict a score. So there is a lack of interpretation of the final assessment with regards to the local alterations in the speech signal. Now, there are some few works which focus on the deep learning, but also the interpretability. And we can find, for example, this work, which transformed a deep neural network. So they incorporated a clinically interpretable layer just before giving a final score for the patient. And this clinically interpretable layer is trained on perceptual scores given by experts. There is an extension of this work which considered these interpretable labels of this layer and used in the place of perceptual labels, they used acoustic features extracted automatically from the speech samples. Now, these works took into account the interpretability of the final score based on these clinically interpretable labels. But the problem is that to train this label, they need extra labels, so extra perceptual labels given by the experts, which can result also in a subjectivity while interpreting the final score, but also they need a large amount of pathological data since they train their deep neural network from scratch on pathological data. Okay, so our goal in my PhD work was to develop an objective assessment tool for speech disorders that incorporates the advantages of deep learning and addresses the limitation of these assessment tools. So we considered the interpretability and explainability of deep learning, the interpretability of the final score with regards to local alterations in the speech signal. We considered the high data requirement of deep learning, but also the fact that in a speech pathology context, we don't have a lot of data, so there is limited data availability in this context. And we had many sources of inspiration. Basically, all the works that appeared in these last years and focusing on the interpretability and explainability of deep learning, which are basically very common in the computer vision field, but also we have a special focus on the speech field in these last years. Now, before I move to the details related to our work, I found essential to focus on the need of interpretability and explainability in a clinical context. So we know that the clinical context is with a high stake context. So a clinician needs to know why the decision made by a system, why the deep neural network gave a given score to the patient. So he cannot just accept this score as a fact. He needs to know what are the linguistic units on the speech that are, for example, less intelligible, and these explain the fact that the patient has a low score. I think this part Jeff already talked about, that there is confusion in the literature. They use interchangeably both terms, and we agree on the interpretability and explainability definitions. So what I am going to present is taking into account that the interpretability is the mapping of an abstract concept into a domain that the human can make sense of, and the explainability is the fact that we want to know which type of representations are encoded within the hidden within the structure of the deep neural network. The data sets we use in this work are basically corpora for speech disorders due to head and neck cancer. The first one is C2SC corpus. It includes almost 100 100 speakers. So there are patients with head and neck cancer and control speakers. And in this corpus, each speaker was recorded for multiple tasks as the reading task. So basically we have one patient and he reads a clinical text, La chèvre de Monsieur Seguin. It's a clinical text used to assess the patient on the reading task. And an expert gives a score for intelligibility and a score for severity. So the scores in this corpus are from 0 to 10, where 0 reflects an intelligible speech and 10 reflects a perfectly intelligible speech. We have a second corpus including 25 patients also with head and neck cancer, and we have a corpus for healthy speech, which is breve corpus. Now, the proposed methodology is based on 3 steps. So we have a patient with his or her recording, and we are going to give him a final score assessing his speech quality. So we propose a methodology for an interpretable assessment of speech intelligibility based on 3 steps, and in the following I am going to detail each step. In this first step, we are going to represent the healthy speech. So we train a CNN for the task of French phoneme classification on breve corpus. It's our reference for healthy speech. And we train it for the task of phoneme classification. And the structure of the CNN is very simple. It's 2 convolutional Poling layers, followed by 3 fully connected layers, and finally the classification layer with the 32 French phonemes classes. As the results of this first step, so on healthy speech, we obtain good classification performance, considering the fact that the classification is made at the frame level. So for each 10 milliseconds, we expect a final phoneme class. So based on this, we have 81.4% on breve corpus for test, and we have 72.2% on the C2SC corpus only for healthy speakers. So this this drop of accuracy is explained by the fact that it's neither the same recording conditions, neither the same speaker, so it's a lot of variability conditions. And we can say that the model is able to generalize well. We analyze the confusion matrices of the classification and all of the we can explain almost all of the errors, so we can say that now we can move to the disordered speech, and we assume that any significant degradation in the classification performance is due to the speech quality degradation. So we evaluate the model on each patient and healthy control speakers, and we analyze the correlation in these 2 plots. So these scatter plots on the right here, we have the severity perceptual measure given by the expert, and on the x-axis we have the balanced accuracy, which is calculated. So it's the accuracy given to a patient. Each point is a green point is a patient, and a blue point is a healthy control speaker. So we can see that there is a correlation between each of the, so the difference between the 2 plots is that the one at the right is the for severity, and the one for the left is for intelligibility measure. So we can see that it correlates well. So the model is able to reflect the degree of speech alteration just from the classification performance. And to conclude this first part, we did the phoneme classification task. So we have insightful information at the phoneme level about the final intelligibility score that we are going to predict in the next steps. And training on healthy speech resolved mainly two problems. So it resolved the high data requirement of deep learning, because we cannot train from scratch on speech pathology due to the limited data availability of speech pathology, and we gained insights into normal speech patterns, which is valuable for later consideration of speech disorders. So we can add a part to our global methodology. With this first step, we have a patient. We fed his or her recording to the CNN, and we have a phoneme representation of this speech on the phoneme dimension. We have also deep representations of the phoneme of phonemes in the hidden layers and neurons of the CNN. I don't know if you have questions for this first step or... Yes.
So if you could go back to the correlation plots a little bit. I was wondering if some other analysis also might be helpful. I was just thinking, for example, in the right plot and the spread, right? So I was thinking that, yeah, there is correlation, but it's not that great. But maybe it's not needed. So what I was thinking is, if you could just take lots of pairs and just look at the rank ordering.
Rank ordering?
Yeah, just whether the balanced accuracy, when it improves, if the severity score also goes up or down, whatever it's supposed to do. The reason being that if you're going to use this to monitor a patient, the absolute score may not matter. What may matter is, can you detect any degradation in their speech and so on. So in some sense, correlation is not the right number for that. You just want to take pairs and ask whether they preserve rank ordering.
Okay.
You see what I'm saying? So I'm wondering if other statistics might be computed to decide how useful this balanced accuracy is. It may be more, I mean, if I look at the plot, yes, I can see a trend, but
yes,
it doesn't look like I can calibrate it and get a number out of it. The spreads are too large. But maybe it's not needed. Maybe ordering is enough.
Yes, it's I mean, the most important in this part is to see that there is trend. So you are right. If it's rank ordering or correlation, we cannot say that there is a correlation of 90 because it's an R value of 0.91. So right. It's a strong correlation, but without visualizing this plot, we cannot say that there is...
Right, and the other question I had was, do you have on this plot any dots that belong to the same patient, or are each dot a different patient here?
Each dot is a patient here, and the blue dots are healthy control speakers.
Okay, so because if you had multiple dots for the same patient over a period of time, that would be another way of looking at this, because there again, some patients might just be harder to, less intelligible than others intrinsically, regardless of their pathology.
But each point, what does it reflect? Classification for a given phoneme? Because we did a confusion matrix analysis also that I don't have here.
No, I guess maybe I'm not asking the question correctly.
Okay.
One dot on that plot.
Yes.
Each dot, does it represent a different patient, or are there multiple dots coming from the same patient?
No, each dot is a different. It's a different patient.
Yeah, okay.
One plot per patient.
One dot.
One dot. Yes. Yes.
Right. Yeah. Okay. So I was hoping that you would have a patient over time,
yes,
or over multiple sessions where.
No.
Yeah.
Wait,
okay.
This is one of the perspective of this work.
Okay.
So we need more data for to do a longitudinal study. to track the progress of pathology a long time for one patient.
Okay, all right.
Thanks. I was wondering, I don't understand balance accuracy. It's something that you calculate for the whole data set. So can you explain the correlation? I mean, I understand on the y-axis you have these scores, but on the x-axis you have different balance accuracy. So
yes, I feed the speech signal from one patient to the CNN. And then I calculate the balanced accuracy for a given speaker. So each point is a speaker. Okay. And it has a balanced accuracy, so it's the mean of the classification per class.
All right, okay, thank you.
Okay. So in this second step, we have a set of research questions that we want to answer. The first one is, can we find a relevant concept that is encoded in the hidden neurons and layers of the CNN from a clinical point of view? And how can we retrieve information related to speech pathology based on these meaningful concepts and representations if they exist in the CNN? And the third research question is how to interpret this information and bring out fine-grained analysis of the speech pathology. So to answer the first research question, we proposed a framework for the explainability of hidden neurons of a deep neural network, which we name Neuro-Based Concept Detector. And to apply this framework, the first condition is to have a representative stimuli dedicated to the explainability and interpretability phase. So here we chose a subset from a brief corpus, which is a representative stimuli. Sorry. Which has to be never seen in the CNN training and validation for sure, and it is its construction is a little bit special. So we have to represent all the phonemes, the French phonemes. And the frame selection criteria are frames have to be related to a complete phoneme production. It has to be a variability of the context and the speakers with equal distribution among all the different phonemes. So in the first step of the NCD, we built representations vectors of neurons. So based on this brief int corpus, the representative stimuli, we fed the different frames to the CNN. I want to specify here that the activation function used in the hidden neurons are ReLU activation function. And for each neuron, we fed all the samples of the trained CNN, and we construct a vector, a representation vector of the neuron N based on the activation values of this neuron to all the samples in the stimuli dataset. And for all the representation vectors of neurons belonging to one fully connected layer, we do a dimensionality reduction via TSNE, and we plot it for the 3 fully connected layers of the CNN. So here, each dot is a neuron. So we have 1,024 dots in each fully connected layer, and we can see that there are some clusters of neurons. So we are wondering what type of information do these neurons encode. Now, as the second step of the neural concept detector framework, we have to fix a concept that we want to explore. In our context, this concept has to be related to the context, so we are in a clinical context, and the chosen concept is phonetic features, which are abstract representations reflecting the acoustic and articulatory characteristics of phonemes, and they are concepts of great relevance in clinical practice, since it can be directly linked to the physiology of impaired speech. So to define this concept, we worked in collaboration with expert phoneticians, our colleagues, and we had these classification. We have this definition of phonemes as a set of phonetic features. So, for example, here the back phonetic feature is related to the position of the tongue in the mouth. If it is the phoneme is articulated in the back of mouth, or if it is not. So if it's 1, it means that it is articulated on the back of the mouth. If it's 0, it means that it is articulated in front. And if it is indefined, it means that the backness phonetic feature does not characterize the phoneme in question. And in the third step, we are going to characterize the neuron ability to detect the concepts that we fixed. So in our case, we defined a score that reflects the degree to which a neuron is selective for a given phonetic feature. So this score is calculated for a couple neuron phonetic feature based on the activation values of this neuron, and we will have a score between -1 to 1. So if we fix a threshold, and if this score is greater than the threshold, it means that the neuron is selective for the presence of the phonetic feature. If it is less than minus the threshold, it means that the neuron is selective for the absence of the phonetic feature, and else the neuron does not detect at all the concept of phonetic feature. So it means that detect other concepts that we are not taking into account in this work. Now, applying the NCD framework to the fully connected layers of the CNN, we take the same plots here, TSNE plots, and we just add an extra variable, which is the color of the neuron based on the phonetic feature that it detects. So here we have all the list of phonetic features, and we can see that there are homogeneous clusters with that there is clusters of neuron with homogeneous colors. It means that these cluster of neuron encode the same phonetic feature. And we have an increasing number of phonetic feature detectors when going deeper in layer. We can also notice the absence of the first fully connected layer, so it's FC2 and FC3, because the first fully connected layer does not has not detectors of phonetic features. So, okay, so we were able to answer the first research question, and the answer is yes. We could find relevant concepts in the clinical context that emerge in the hidden layers of the CNN, which we can relate to the physiological characteristics of impaired speech. And this was given I mean, we could find this because of our first main contribution, which is the NCD framework that we published in ICASP 2022. Okay, so we were able to add another piece of puzzle here, and we are focusing on the two other research questions. So if you have questions about the previous part, you can ask.
So what about people who have a different accent, even they
Yes.
will have different phonetic pronunciation, or there will be a lot of phonetic variability?
Yes.
How would you distinguish people's pronunciation which is caused by an accent or by some pathology or illness?
Okay, actually, I will show in the next step, I will show a remark that is related to your question.
I was a bit sleepy, so I didn't really follow the way how you could associate the neurons to these phonetic features. Could you go through it one more time, please?
Yes. In this one?
Yeah. Yes.
Okay. So it's based on this score.
Yeah.
Okay. I prepared some slides for the details of this score, but I will show in the session lab. So
Maybe just in high level?
Yes. So basically the first part of the score reflects the activation level of the phonemes that present the phonetic feature in question. So it means that here the phonemes O, U, on in green, which presents 1 for the back. If we are calculating the score for neuron N and for the backness phonetic feature. So we are taking into account the activation values of all the frames that have as true label the back phonemes against all the activation values of this neuron N to all the rest of phonemes that do not present the back phonetic feature.
All right.
And
okay.
in this way, with the threshold, if if the score exceeds a given threshold, it means that the first quantity is it's bigger than the second one, and so the neuron is considered as a strong detector for the presence of the phonetic feature. And if it's each less than minus the threshold, it means that the neuron is a strong detector for the absence of the phonetic feature. Okay. So in this part, we want to know. So now we have identified the neurons that are detectors for the concept of phonetic features, and we know each neuron is a detector for which phonetic feature. And at this level, we want to conceive a method that with which we want to retrieve information related to the speech pathology based on these neurons, detectors of phonetic features, and we want to see if these interpretations can give us relevant information on the speech quality. So to this end, we propose a scoring approach, which we name artificial neuron-based phonological similarity. So this score, INPS score assess how well the acoustic and articulatory characteristics related to a given phonetic feature are produced by a given speaker. So it's calculated for each couple S speaker, T phonetic feature. So basically this score is based on the set of phonetic feature detectors, and for the set of speaker we have a speaker patient 1, for example. We are going to calculate how well this patient 1 is producing well the voiceness phonetic feature. So we are going to compare it to the activation values of the activation values of all the detectors of the voiceness phonetic feature compared to the activation values of all the voiceness detectors for healthy speech, which is our reference, which is bref int. So this formula will give us a score varying from 0 to 1, where 1 reflects a typical acoustic and articulatory characteristic for the given phonetic feature, and 0 means that the patient 1 does not present typical acoustic and articulatory characteristics for the given phonetic feature. And we calculate we do the same for one patient for all the phonetic features we have.
Have you tried also weighting the contribution of individual neurons, because each one acts as a different quality of the detector for the feature? So if you tried it, or if you argue that if you have enough of them, it somehow merges up?
Yeah, by contribution you mean, for example, the score?
Yeah, they had a score for detecting the feature of, for example, nasality.
No.
Yeah.
We consider that if the score of the neuron exceeds the threshold, it means it is detector, and we do not. But maybe it's interesting to add another factor reflecting the contribution of the neurons to detect a phonetic feature. Okay, so with this step, we have a set of scores reflecting how well each patient is producing each of the speech phonetic features. And to visualize these scores, we chose to plot it under the form of a heat map. So in the x-axis, the y-axis, we have the set of phonetic features. So here it's the subset of vowel phonetic feature, because we consider the vowel and consonant as separate. So these are the set of vowel phonetic features. And in each column we have one patient. So we plot the INPS scores for one patient based on this color scale. And if it's dark red, it means that the production of this patient for this phonetic feature is very degraded. And we do the same for all the patients. We have the set of C2SC leg corpus patients here and healthy control speakers sorted by severity. So we can see that cells with high opacity are concentrated in the left side of the heat map, whereas here we have more white values of phonetic white colored cells, because this set is the healthy control speakers, because it's sorted by severity level. And here I want to mention that the nasality, in fact, it's the remark made for the accent, and it's because C2SE patients are come from the southwestern of France, so they have a special accent where they do not where they denasalize the nasalized vowels. So for a nasal vowel, on, for example, they aim to pronounce it as a combination of an oral vowel, O, and a nasal consonant, N, O, N, on. So it's, we can detect this accent phenomenon because even for the healthy control speakers, we have here red cells, so we could explain it by this explanation. Okay, and now we want to interpret this heat map. So all of these patients are head and neck cancer patients. We can see that among the phonetic features, we have the plus high phonetic feature, which is impacted, and mostly the back phonetic feature. So both these features are related to the tongue movement in the mouth, which is the more impacted for head and neck cancer patients because of surgery on the tongue. And so it means that the INPS score reflects the strong relationship between impaired speech due to head and neck cancer and the tongue movement. We also validated this with the correlation analysis, and we observed the same trends, but also we tested on other speech disorders like dysarthria, Parkinson's disease, and we have interesting results reflecting the alterations in phonetic features in relation to some characteristic of the speech pathology. You can find these results in this interspeech paper. And with this INPS score, we were able to answer the second research question, since we could retrieve informations based on the set of neuron detectors for phonetic features. And we are also able to say that we can retrieve fine-grained interpretation of speech impairments. So with the explainability phase, we bring to light an interpretable dimension, which is the dimension of phonetic features that was automatically encoded by the CNN. And with the interpretability phase, we provided a fine-grained interpretations of the speech impairment based on this emergent dimension, and we ensured an additional level of granularity for clinicians to interpret the final assessment score. So in this, the last step, it is our final goal, the final assessment of patients. And here we want to see if we can predict a global score assessing the speech quality of the patient based on the outcome of the two previous steps, and how we can link this final assessment and interpret it in terms of the interpretable dimensions. So in the whole architecture, we have a patient, and we extract the feature, the signal features of this patient. We feed it to the CNN-based phoneme classifier, and we extract the logit vectors of the phoneme classification task. And then we fed it into a shallow neural network for a final score prediction. And we have a scalar score for each 1 second of speech. And we do this process for each 1 second of speech. To have a final score for the patient, we average the set of these scores. Now, in the second method, we are not based on the logit vectors, but we are based on the set of phonetic features detectors. So here we do the same thing, but just for the final score prediction, which is based on the phonetic feature embeddings. And the final task, regression task, is very simple. It's one fully connected layer preceded by an average polling layer that we train for two tasks. The first task is intelligibility prediction, and the second task is severity prediction. It's the same training set, training and validation sets, but to predict two different scores. Now, to evaluate these regression models, we used MSE and MAE, and we could find good results, since with in the intelligibility prediction task it's 1.2. So the interesting here that for a given patient, the patient is assessed by 6 experts. Sometimes we can find a difference between 2 experts that exceeds 2 points on the scale of 0 to 10. So if the model is able to predict with 1.2 error, it means that this error can be observed as a difference between 2 experts. So it's acceptable. And now to analyze the model prediction of the model prediction on C2SC corpus patients, we see that there is a correlation between the mean predicted severity by the regression model on the severity prediction task and the perceptual severity given by experts. So the model are able to capture some of the underlying patterns in the phonetic feature embeddings. However, we have some phenomena that we know, with which we know that there is piece of amelioration for these models, as the fact that it underestimates the high severity scores and overestimates low severity scores. And we observe the same trends on the test set. So we are able to answer the research question. Yes, we have promising results on the task of speech intelligibility assessment for patients with head and neck cancer. And the final step now is that we want to see in clinical application how all this method can be applied. So here I'm supposed to have a recording for the patient, but for confidentiality problems, since we are recorded, I cannot play it. So this patient, CFW16, we fed her recording to the proposed methodology for an interpretable assessment of speech intelligibility, and the method give a predicted speech intelligibility score of 5.52. And here we have the metadata of the patient. So it's her clinical data. So she has a tumor location on the oral cavity, and she has a tumor on the tongue with a T4. So T4 is the bigger tumor size. It's T1, T2, T3, T4. And she has been subject to pelvic glossectomy. So basically, it's taking off a part, the back part of the tongue with surgery. And she has perceptual measures of intelligibility. The intelligibility is 5.8, and the severity is 5.6. 16. So 5.8 is a little bit, it's not too bad, the prediction given by our model. And we are able to interpret this given score by the confusion matrix. It's not very clear here, but it's actually the true labels of phonemes and the predicted labels by the model. So we can see that the B phoneme is absorbing the D and G. So every phonemes that she tries to pronounce and as D and G, she pronounces it as B. So here we have interpretations at the phoneme level, and for the interpretation at the phonetic feature level, we can see that she has the most impacted phonetic features are the compact and acute phonetic features, and back for vowels, which reflects once more a problem in the tongue. So we can interpret the final assessment scores based on the two dimensions of phonemes and phonetic features. And to conclude this part, to conclude all the presentation, we proposed a three-step methodology based on deep learning and dedicated to an interpretable assessment of speech intelligibility in the context of speech disorders. We addressed the lack of interpretation of the final assessment with regard to local alterations, since we proposed a method that gives insightful information about the score at both the phoneme and phonetic feature levels. We addressed the problem of interpretability of deep learning, which means that the black box characteristic is mitigated, and we alleviate the mistrust among experts in a clinical context. This work has many perspectives. So as a longitudinal study, we can imagine it to track the change over time in the speech production of patients to evaluate the interest of speech therapy. We can imagine it also to take in non-clinical applications such as a second language. For example, someone who tries to learn a second language, we can give interpretations to identify the phonetic features that the speaker cannot pronounce well. So in e-learning platform, it can gives him a recommendation to focus on these phonetic features, and it can be imagined in some regional accent, in some application which needs to identify a regional accent. And for the NCG framework, so it's a general, it can be applied to any neural network to identify any concept in the hidden neurons. So we can imagine it on different architecture for different tasks, for different concept identification. These are all the references I used, and thank you.